Hello everyone, this is Sina here, and today I'm glad to present our research to you entitled as What Distributed Systems Say, a study of 7 Spark application logs at SRDS 2021. This work has been done as a part of my PhD research at the University of Waterloo, Canada, with collaborations from my supervisor, Dr. Paul Ward. So let's get started. Let's first review the agenda for today. I initially review the motivation behind our research in analyzing software logs. Then I explain our research approach, followed by our research questions and findings. Our research main goal is to find the relationship between logging cost, verbosity levels, and the amount of information gained from software logs. And finally, I summarize and conclude my presentation with key takeaways. First of all, let's talk about our motivation. Why logs? Developers and practitioners spend a significant amount of time writing and reviewing logs. For example, log files are widely used to record runtime information of software systems, and the rich information of logs enables system developers and practitioners to monitor the runtime behavior. On the other hand, although extensive logs are helpful to provide valuable details to identify the root cause in postmortem analysis in case of a failure, this may also incur performance overhead and storage cost. The problem is further exacerbated in distributed environment that various nodes simultaneously generate a large volume of logs. Thus, to address these trade-offs associated with the overhead of logging, well-known libraries such as Apache Log4j provides facilities for different levels of logging. The libraries provide different verbosity levels such as info, trace, debug, and so on to dynamically control the amount of logging statements being ultimately outputted to the log file on the storage medium. This figure shows an example of a logging statement from Apache Spark source code with info verbosity level and also its end product in the log file. In addition, each logging statement consists of a constant part, i.e. executor added on the cores highlighted in blue, and the variable part such as full ID, worker ID, etc. Thus, considering the flexibility that each log level brings, our goal in this research is to quantitatively measure the cost in terms of storage, execution, overhead, and information gain of log files while the distributed system is running under different log verbosity levels and also during failures. More specifically, we guide our study for logging cost and benefit with the following research questions. In research question 1, we analyze the quantitative cost of logging in terms of computation time (CT) and storage overhead (SO). In research question 2, we investigate how much information is gained from different log verbosity levels (VLs). And in research question 3, we examine how the characteristics of logs change with distributed failures, such as compute and storage node failures. Does the entropy or information gain of logs increase when a failure happens? Our research provides practical findings on how to choose the level of logging and ultimately control the amount of generated logs and the information gain, and how the distributed failures can be detected with observing entropy values. In our setup, we run 7 Spark benchmarks with different log verbosity levels and calculate the execution times and the size of the generated logs. We then utilize Shannon's entropy theory and N-gram models to measure the information gain by calculating entropies for different log levels with and without failures. We evaluate the benchmarks on a cluster of 4 commodity machines illustrated in this figure, with 1 Spark master and HDFS name node and 3 nodes which host Spark slave nodes and HDFS data nodes. This table summarizes the benchmarks used in our experiments along with their characteristics, such as being CPU or IO intensive and if the computation happens iteratively. During the benchmark selection, we were deliberate to include a variety of workloads such as Spark's conventional benchmarks like word count and PageRank, and machine learning ones such as gradient boost classification and linear discriminant analysis or LDA for clustering. Here I provide you with some results for research question 1 with regards to logging cost in execution time and storage overhead. The top row shows the computation time for different benchmarks for different log verbosity levels, and the bottom row shows the storage overhead of logs. Overall, we observe on average around 8% increase in execution time and 268 times overhead in storage when the trace log level is enabled versus the info level. And CPU intensive workloads suffer more from a higher degree of logging. Also, due to the high level of repetitiveness in log files, they can benefit from large compression ratios. Thus, the noticeable difference in storage cost can be mitigated by the compression of log files to 43x. Generally, logs are stored on a storage medium such as hard disk drive or solid state drive, which might be one of the factors of the execution slowdown when logging extensively. Thus, we also experimented with a faster storage medium, meaning that writing and storing the logs to a RAM disk instead of the hard disk drive. We observed that faster storage mediums can mitigate some of the execution time overhead associated with logging for CPU-intensive workloads that generate significant amount of logs in more verbose log levels. In research question 1, we observed that higher degree of logging contributes to additional system overhead and cost. Here, in research question 2, we investigate whether this additional system cost is translated to more effective logs, meaning that are more verbose logs more effective? Log effectiveness is a quantitative measure of logs in being effective in achieving their goals, which is in our study, diagnosis and troubleshooting. Shannon's entropy is used to measure the amount of information that is contained in an information source, for example, a log file. Entropy is calculated as in this formula where Pi is the probability of a possible character happening in the log data. The higher the Shannon's entropy, the more information in the file under analysis, and the lower the entropy, the more deterministic the content of the file is. In addition, prior research has shown that log files and log messages are natural, meaning that natural language models such as n-gram statistical models can be applied to describe the sequence of tokens in log messages. Thus, the probability of observing AI in the sequence of n tokens can be calculated in the formula as the conditional probability of observing preceding I-1 tokens, AI-1, AI-2, and so on. Because in this study, the log effectiveness is directly related to entropy values, the less repetitive the content of the log file, the higher the entropy and the amount of information in the log file. Thus, we utilize Shannon's entropy to measure the entropy values for the sequence of log tokens to measure the log effectiveness. Let's revisit the log example. In this example, log statement consists of two parts, static part in blue and the dynamic content. Static content of log statements originate from the source code, and the dynamic content is the value of variables that are printed in the log files as the system is running. The common perception is that higher degree of logging translates to more effectiveness of the logs. For example, logging in trace level is more effective than info level, which we argue this assumption might not completely hold true. To measure the amount of information for different log verbosity levels, we train different n-gram models and measure the entropy values. The size of n describes how many prior tokens are considered for predicting the next token. For example, in a 5-gram language model, the fifth token is predicted based on the preceding 4 tokens. In the plot here, the x-axis shows the incremental sizes of the n-gram models, and the y-axis shows entropy values for trace and info log levels, as well as natural language text such as Wikipedia articles and Gutenberg text. The observation is that log files have a lower entropy than common English text. In addition, the entropy values stabilize at around 4 or 5 n-gram models. Our results show that although trace level generates larger volume of logs, trace data does not provide a noticeable high entropy, and hence does not necessarily carry higher information gain and effectiveness when compared to less verbose log levels such as info. The implication is that trace logs show comparable information gain to info level because they contain higher repetition rather than unique dynamic values. So far, in research question 1 and 2, we discussed the cost associated with logging and the log effectiveness. We know that logs are commonly used for failure diagnosis. Thus, in research question 3, we evaluate the information gained from logs in injected failure scenarios. We design a framework to inject different types of distributed failures and measure their impact on logs and how the information gain and effectiveness of logs changes in the presence of failures. We categorize the distributed failures in 4 main categories: compute node failure, storage node failure, communication interference, and combined failure, which can be a combination of multiple failures. The plot here shows the entropy values as a compute node failure happens. We observe that failures result in a region of higher entropy values compared to normal entropies in the log files. And different runs show extended computation time and additional logs related to the failures. Computation time of CPU-intensive applications suffer more from compute node failures than I/O-intensive benchmarks and so on. Thus, the implication is that sudden changes in the entropy values of log records can signify an information gain associated with a system failure. This information can be leveraged for pinpointing the failure from the logs. Thus, for debugging, we are more interested in the region of the logs with higher entropy than logging in trace level. We continue with an example of data node failures for word count, which is an I/O intensive benchmark, reading and writing approximately 52 gigabytes from and to the HDFS. The results show the entropy values on the y-axis over time for the name node and 3 data nodes as the failure happens. When data node 4 fails at log window approximately 70, we observe a delayed manifestation of entropy changes in other data nodes, data node 2 and data node 3, which starts at approximately time window 100. The reason behind increasing values of entropies is because other data nodes are trying to access the data which was available on the failed data node and end up being unsuccessful, and the log messages associated with the failed requests have higher entropy values. From this experiment, our observation is that I/O intensive applications that read and write large volumes of data to the distributed storage will be negatively affected the most as a result of a storage node failure, whereas CPU intensive applications, i.e. with minimal read and write to the storage, will be less impacted. This implies that entropy-based anomaly detection approaches can be applied for online log analysis to isolate the higher entropy regions and further investigate the failures. Here we include some of the results for communication interference and combined failure. The graphs show the computation time on the y-axis for word count and transitive closure benchmarks as the loss probability increases on the x-axis. Here we have implemented Gilbert-Elliott network interference model to introduce communication uncertainty as the packet loss probability. The GE model offers a more realistic emulation for network impairments rather than simple packet loss. The model consists of 2 states, good and bad ones. In this example, the error rate probability in good state, i.e. 1 minus k, and bad state, i.e. 1 minus h, are configured in a way that the packet loss probability is higher in the bad state. And there is a probability to transition from good to bad, i.e. p, and from bad to good, i.e. r. In these experiments, we increased the error probability in bad state from 0% all the way to 45%. We observed that the impact of the combined failure, which is in this case a failure of one compute node and one data node simultaneously, which results in higher computation time compared to no failure, which is reasonable as the remaining nodes need to do more work to finish the benchmark. However, as the communication interference increases, the computation time increases, and the communication interference is manifested as a performance degradation and not a complete failure. We also observe that when the interference or the loss probability increases beyond a certain threshold, the negative impact of performance degradation surpasses the impact of a complete failure, because for each stage of the computation, the faster nodes are evading the completion of the slow node. This observation implies that distributed scheduling algorithms that can detect slow nodes in the system and remove them from the computation can benefit the entire system's performance. As a case study, we also investigated logs collected from real abnormal scenarios for Openstack. The results show the timeline of 52 log windows with 4 injected abnormal Openstack VM sequences in the center for log windows 24 to 27. There is also one false positive high entropy value at log window 17. By leveraging an outlier detection approach, we can reach high F measure and balance accuracy scores as noted here. This signifies the effectiveness of the information gain approach that is achieved by measuring entropy values of log sequences in detecting Openstack's abnormal scenarios. We also measured the computation time of the entropy calculation for a log window of size 4 kilobytes and received on average 2.4 milliseconds execution time in our setup, relatively as long as the execution time of measuring entropy for a log window is faster than the rate of the log generation. The log records can be tested in real time and observed for the amount of the information gain and potential anomalies. And finally, I summarize our research takeaways. In research question 1, we showed that more verbose logging introduces on average 8% higher computation time and 268 times larger log size, which causes storage overhead. This finding provides insight into how the practitioners can adjust the level of logging considering the performance overhead that is tolerable for them. In research question 2, we measured the entropy values in different log levels to assess the amount of information gained for each level, and we observed that the more verbose levels do not necessarily translate to more effective logs. It might just be higher repetition of logs. And finally, in research question 3, we observed that the failures result in peaks in entropy values during the runtime. As such, we suggest to focus the debugging efforts on the log regions that are manifested as larger than normal entropy values rather than focusing on enabling more verbose logging levels for the entire duration of the application execution. We also showed that some types of failures that manifest as performance degradation are hardest to detect, and at some point, the impact of performance degradation can be higher than fully disabling a slow node, which can be an area of future work and optimization for distributed cluster managers and schedulers. We have started to maintain our execution logs in the following link to enable future research, and we encourage you to read the paper for additional details of our findings. And feel free to email for any questions. And finally, I'm glad to conclude my presentation by thanking you all for listening. Thank you.